Cool stuff. Guys, love math. So let's go through what the real number system's all about. But before we start actually classifying real numbers or numbers within the system, let's actually define the system and how did we actually come about getting it. When I say we, you, me, as children at one time in our life started watching one of the best TV shows of all time, and that was Sesame Street. And we learned to count by one. That's ugly. Let's fix that. We learned to count one. That's still ugly. I think I know what the problem is. My tablet is at a tilt. I'm fixing it right now. And we're going to go with 1. Yes, 2, 3, and 4, and so on. Because we learned by Sesame Street how to count up to 10. Oh boy, how exciting that was. We called those our counting numbers basically because we were learning to count. So these are our counting numbers, Dean. And I'm going to box up our counting numbers here. You guys might want to do the same thing. So let's box up the counting numbers here and say, hey, these are our counting numbers. But, you know, a couple years went by and you became real sophisticated guys. And you moved on from Sesame Street and you said, it's time to start watching this other show called Barney. And when you started watching Barney, you realized something else with your sophistication. 1 was not the only number and it was not the first number. In fact, we began starting to count with, what do you think, Mr. Who's going to say it? Who's going to say it? How about Taylor? Yeah, Taylor's saying, hey, I learned to count with 0 when I started watching Barney, but I'm writing in green and I don't want to do that. I want to write in yellow, keep it all the same. So let's write 0. 1, 2, 3, and so on and so on and so on. And you probably even got up to counting to 20 with Barney. Well, let's move forward from there, because Barney would want us to. He'd want us to grow up and go on to our next stage of life. But before I do, hey, guys, guess what? I need to label what I actually call these numbers. And these numbers we call our whole numbers. Barney told us to be a whole person, you have to count the whole numbers, including 0. So the whole numbers, when I take 0, that's a Z, and add it to the counting numbers or the natural numbers, we'll say counting numbers, I end up with, I'm writing count for short, but it's the counting numbers, I end up with a whole new set called the whole numbers. So guys, tell me real quick, Miss Alex, does the whole number system include my counting numbers? Yeah, what's different with it? The whole number system has a 0, counting number system does not. So now let's move forward from here, because I know a couple of years went by still and your parents started saying, hey, you know what, this kid can travel, they're smart, let's get him to go visit our family up in Alaska. You guys probably grew up in Texas your whole life. You were able to count from 0 up to 20 and so forth, but you traveled and you decided, hey, let's go visit some friends and family all the way up in Alaska. So you spent all the cash and dough that you'd been saving over the years. You busted your piggy bank and you realize that, hey, I'm out of money, and it is freezing in Alaska during the winter time. In fact, it's not 0, it's below 0 here, so you start writing your negative numbers, and you say, hey, it's cold, it's chilly, I need to buy a jacket, but I have no money. In fact, I got to go borrow money, and since I had no money, I have less than no money now because I'm borrowing money, so therefore, I've got negative money in my bank account or in my savings. So you realize there's this whole new world of numbers that are called negative numbers. I'm going to get rid of that by now. So you've got this whole new set of numbers called negative numbers. And our negative numbers, rather than calling it negative numbers, because we're also including what, guys? We're including our whole number set. We're also including our counting numbers. So we're going to call these integers. All these integers. And Lila, just like before with the whole numbers, I'm going to end up boxing up my integer set here. Whee! Boy, that's exciting. Okay, from here, guys, you're still growing up. In fact, you probably moved on to the 3rd grade by this point, and you realize, maybe you're even older than 3rd grade, but you realize there's only parts of things. And rather than I don't know, maybe you want to go celebrate. You want to go on a date, buy a pizza for somebody, or you want to go and celebrate a birthday. So you're gonna have a cake or some brownies, and you realize, hey, I'm not gonna eat this whole thing. I'm only gonna eat a part of it. So we'll get my yellow out again. I keep writing in green. But hey, you got 0. We've also got our negative numbers we've dealt with here. But you're also moving on to say, hey, rather than having a whole piece of something, or I'm only gonna have a part of it, so I'm only gonna get a quarter of the cake, or a half of the pizza, or 2/3 of something. Guys, what am I creating here? Creating fractions, and then I actually get to a whole number finally. And in fact, some fractions create a whole number. But I end up with fractions here and decimals. But let's look at this real quick and see what I'm going to. I'm saying, hey, if I have an integer and another integer, and they're creating ratios, because, hey, a fraction is 2 integers making a ratio, an integer in the numerator, an integer in the denominator. Those are fractions. Therefore, we're going to call these rational numbers. And rational numbers have also include, we can see from here, if we break down the system into small little parts, rational numbers include integers, whole numbers, and counting numbers. Again, let's bridge on. Make that big. There we go. Hey guys, but broken apart from, disconnected from rational numbers is this whole wacky set of numbers, not wacky like a bod, but just wacky. They are wacky because I'm going to call them irrational. They're sometimes irrational, like some of the statements Fletcher asks me. When I say, hey Fletcher, what's the square root of 9? And he says, can I go to the bathroom? That is an irrational statement because he's not answering my question. So when we deal with irrational numbers such as this, let's look at, we'll say, hey, pi is irrational, you don't know why yet. Or the square root of 3 is irrational, you don't know why yet. Or the square root of 10 is irrational, do you know why yet? No. But you'll find out. These are all irrational because they create decimals that are non-terminating. Or non-repeating. Hey, Aaron, here's a wacky question for you. Actually, it's not as wacky as these irrational numbers, but if irrational numbers are irrational because they have non-repeating or non-terminating decimals, what do rational numbers have to have? Yeah, they have decimals that terminate or decimals that repeat. You are a genius, girl. Good job. So I'm going to put a box around my irrational numbers. And it's disconnected from, it's not a part of, the rational number system. However, there's this whole other set of numbers, Dean. If you look up there, you'll see this, bud. This last part, all of these numbers, all of the rational numbers and subcategories below, plus the irrational numbers, they create a much larger system called the real number system, or real numbers. So irrational numbers are a part of the real number system. Rational numbers are a part of the real number system. And I can box that up here and say, hey, look guys, they're all within the purple box, the real number system. So they are all a part of the real number system. And you can see that right here. Okay, let's move forward from here, guys. Let's actually scroll down some. We'll start working some more here. Let's look at the square root of 3. Guys, if you look at your notes, or you look at mine, you can tell me that the square root of 3 is what, Fletcher? Don't tell me you need to go to the bathroom. Square root of 3 is where, buddy? Okay, Cameron, help out. Mr. Cameron B, where is the square root of 3? What? Or where? Where? What system is it under?
What system?
Yeah. It's irrational, baby. Look at that, guys. No, 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 no. Do not be crazy. Do not be irrational. I'm not asking you to solve it. I ask you to say, hey, where is it? Right here, buddy. Look. Right here. You got it? Okay. It's irrational. Hey, Brooke, if it's an irrational number, what is an irrational number a part of? What? Yeah, it's also a real number. So therefore, the square root of 3 here, it's going to be irrational or real. Or I could say and real because it's both. But let's figure out why. Don't just take my word for it. So let's figure out why it is. Because it should, if it's irrational, it should have a non-terminating or non-repeating decimal. Well, let's figure out why. There we go. So this is my number line. It kind of started off bad. But if you see it, here's the arrow going left. Let's take a look at the square root of, let's take a look at the square root of 1 and the square root of 4. Hey, Dominique, square root of 1. Yeah, so on the number line, it's 1. Square root of 1 is equal to 1. And Miss Mary Beth, square root of 4? Yeah, so on the number line, hey, this is 2. These are two consecutive numbers, 1 and 2. 1 and 2 are right next to each other. But the square root of 1 and the square root of 4 have also got to be next to each other on a number line, don't they? They are two integers here, 1 and 2. However, look at the square root of 3. It falls in between the square root of 1 and the square root of 4. Therefore, it has got to be a number, the number 1. It's got to be in between 1 and 2. So it is 1 point, Fletcher, something, something, something. I really don't know what it is, Fletcher. Just like you, I don't know how to solve it without a calculator. I don't. I do not know how to solve the square root of 3 without a calculator. But I can tell you, since it's not a perfect square, the square root of 3 is not a perfect square. Therefore, it has got to be irrational. Square root of 3 is not a perfect square. Therefore, it is irrational. So if I look at this another way, because I told you, hey guys, I can't calculate it, but I can say it's not a perfect square. Why is it not a perfect square, Miss Abby?
Because some square is when you start on the square.
Because the integers to the left and right of it are consecutive perfect squares. Why are they consecutive? Because 2 comes right after what? 2 comes right after 1. That makes it they're consecutive. And 3 is in between those consecutive numbers. Therefore, it's got to be a decimal. Right? Yeah. Okay, cool. But guys, like I said, I cannot solve this without a calculator. Fletcher can't solve it without a calculator. Nothing wrong with that. We're cool guys still and totally comfortable with our masculinity still. We are not embarrassed. Therefore, we're going to calculate here the square root of 3. We say the square root of 3 equals, guys, for this to work out, for it to be irrational, it has to be a non-repeating, non-terminating decimal. And we see up here that the decimal is 0.7320. Fletcher, you're looking over here? Cool. The square root, it is, the decimals are not repeating here. They are not 0.777777. And they are not terminating because they fill up the screen and probably continue. They got blocked off by the wall here. The calculator couldn't put any more numbers on. Therefore, we're going to shrink this and go back to say it's irrational, and we're going to look at another one because we killed that problem. Do-do-do. That's the ugly line. Fix it up. Do-do-do-do-do. Brooks a cool student. Do-do-do-do. All right, everybody, stand up real quick. Shake your arms and legs out. Take a deep breath in. Let it out. Okay, have a seat and look at the value up here, negative 56.58. Negative 56.58, Mr. Sam, tell me, does the decimal repeat?
No.
No, but guess what, buddy? Does it terminate?
Yes.
Yeah, it stops after the 8 here, so therefore it has got to be what type of number? It is rational. Wait, who said that? Fletcher? Sam? She said rational for you. She helped out. It is a rational number because it does terminate after the 8. However, Sam, it is also one other type of number. Can you tell me what it is? If it's rational, it has to be. Go think big. What is the rational number also wrapped around by? What wraps around a rational number?
Real number.
Yeah, so it's also a real number. However, is it an integer, Sam?
No.
No, because integers aren't including decimals, buddy. Rational numbers include decimals, and it's a terminating decimal. So let's scroll down, and we'll say, hey, this dude is totally rational. And it's definitely real. Take a look at another one. Let's look at the square root of 9 over 3. Cameron P., what is the square root of 9? 3. So you end up with 3 over 3. And Maddie, what's 3 over 3 equal? 1. So Bailey, if you look over here, if you look at 1, you could say, hey, 1's my answer. So let's go up and find out where 1 falls under within our system. Tell me, does it fall under a counting number? Yep. How about a whole number? Absolutely. Integer? Rational number? Therefore, it is absolutely a real number. However, Mary Beth, is it irrational? No, it doesn't have a non-terminating or a non-repeating decimal, right? It's just the value 1. Great job. Hey, Nazim, I already forgot what I told Mary Beth. Why is 1 not an irrational number? You got 2 solutions of why it's not. Yeah, the decimal for 1 terminates, and there's actually nothing behind it that repeats, I guess, unless you want to say there's zeros, 0, 0, 0, 0. But it is actually, guys, like we said, it's counting, whole, integer, rational, and real. Hey, guys, by the way, I am not going to test you on counting numbers. I just wanted you to understand where counting numbers came from, and I like to talk about Sesame Street. So we'll start at whole. We'll start by saying it's a whole number, an integer, a rational number, and a real number, Cameron. It is a whole number. It is an integer, a real number. Oh, before it's a real number, it's got to be what? Rational, therefore it's real. Awesome. All right, so this is our answer. Now we get to go on to the next problem. Let's actually determine whole numbers. Or not whole numbers, let's determine all numbers. Let's look at the square root of 10. Square root of 10 here. Well, guys, like Fletcher said earlier, I cannot calculate this, but I do know if I draw up a number line, we'll take a look here. There's 0, arrows, theme, focus. If I were to ask what's the square root of square root of 9, and let's, hey Bailey, what's the square root of 9? 3. Yeah, absolutely, it's 3. And Dalton, what's the square root of 16? So it's 4. Hey guys, do I have 2 consecutive roots here? Yep, I got 3. I got 4. And I know that 10, since 10 falls right in between there somewhere, the square root of 10, Is it going, can I have a perfect square? 9's a perfect square. The square root of 9 is perfect square. Square root of 16 is a perfect square. 3 and 4, there's no integer that I can use in between here. So therefore, the square root of 10 is what? It's not a perfect square, so therefore it's what? D, absolutely. Who else said that? Who else said irrational? Good job, Dalton. It's not a perfect square, so therefore it's got to be irrational. So this is irrational. And let's figure out why. Well, I know it's got to be at least what? What's the number it has to start with? It has to be 3 point something. I don't know what it is, but let's figure out here. Unit 2, square root of 10. Square root of 10 is, and Dean, you're going to help me out with this one, buddy. Is that decimal repeating? Is it 0.1111?
Nope.
Nope. What about, is it terminating? It gets blocked off by the wall. It's not terminating, okay? Lila? Since it's not terminating, it's not repeating, it has got to be irrational. We already said that. Great job. Okay, now, let's move on. Since it's irrational, Fletcher, nope, take that back. Kathleen, since it's irrational, what is it? What other number can it be? What other type of number can it be? Irrational, it can be. Irrational is also a part of the what system? Yeah, it's also a real number. Is it a rational number too? So it's also a real number. Okay, another problem. Let's look at 3 divided by 0. Hey Alex, what's 3 divided by 0? Well, let's look at this real quick. Let's write it in long division. That looks like a square root. I don't want to do that. Let's write it in long division here. We'll say the square 3 divided by 0. Guys, the thing to ask yourself here is how many times do I multiply 0 to get to 3? What do I have to multiply 0 by to get to 3? Brooke, what can I multiply 0 by to get to 3? You can't. So, therefore, it is not a real number. Guys, if it's not a real number, guess what? It doesn't fall within the system anywhere. It's not a part of this system. So let's scroll back down. Let's take a look at another one here. And we'll look at the square root of 1 over the square root of 4. One over 4, Lila. Hey, Lila, what's the square root of 1? What's the square root of 4? So 1 over 2, and I can prove that right here, because 1 over 2 times 1 over 2 equals 1 over 4. If that's the case, then I know the square root of 1 over 4 is got to be 1 over 2. That's a multiplication symbol, guys. Okay. 1 over 2 equals what as a decimal of odd? Yeah, it's 0.5. Well, what 0.5 inside of my real number system lands where, buddy? Where would 0.5 land? It's a fraction, so it has to be what type of number? It has to be rational or irrational. Which one of the two? So I'm going to write it, Alex, Dominique. 0.5 is either rational or irrational. So you got to ask yourself, does 0.5 repeat? The decimals, do they repeat? No. But do they terminate? 0.5, does it terminate? Huh? 0.5. Are there any decimals after 0.5? Let's take a look. You don't sound too sure, so let's figure it out. Let's just look at it. Is this repeating after the 5? No. So does it terminate? Yes. Therefore, if it terminates, it is what type of number? It's rational, and rational numbers are part of what system? Yes, you rock. It's rational, and it's real. Fletcher, stop. And it's real. Let's take a look at one more here. This is a cool one. It's been tricking everybody all day long, so let's see if you guys can get it right. Let's take a look at the square root of negative 17. Oh, yeah. Square root of negative 17, and Aaron is up. Okay, Aaron, you're up, kiddo. Square root of negative 17 is what? Great, I'm glad you don't know. Fletcher, let's ask Fletcher real quick, and we're going to look at the negative number inside the square root symbol. Cameron B's got his hand up. What's up, Cameron? What? Wait, don't look at me. Tell your class. It's not possible, which means what, Fletcher? It is not a real number. Guys, the thing to ask yourself whenever you see a square root is what? What times itself? What times itself equals a negative number? Nothing. Therefore, it is not a real number. Does that mean that it's an irrational number? If it's not a real number, is it irrational?
No.
Why not? Why?
Irrational real.
Irrational? You were getting candy for that one. Awesome job. Because an irrational number is a real number. It's within the real number system. Not a real number is not in the real number system. Get it? Good. All right, so let's move down. We're going to look at one more thing to solving problems. We're going to look at something called, this is huge, guys. If you get this, this is huge. And then I got something to talk about with you about the last 5 minutes. Remind me, guys, we've got something to talk about the last 5 minutes. Fair enough? It's about this, the density property. We're going to call this the density property. And what the density property tells me, fellas and ladies, the density property tells me this. Hey, if I've got two numbers, so let's take a look here. If I've got two real numbers, right? Let's take the number 2 and 1/3. And let's take another real number, 2 and 2/3. So if I have any real numbers, it tells me there are many solutions to, I'm going to take that back. There has got to be another number halfway between these two real numbers. If you have two real numbers, there's another number halfway between these two real numbers. But how do we find that? So the first thing I'm going to do is draw my number line. Oop. Forget that last piece. I don't like that it popped up. But here we go. You all right, Lila? All right. So we've got here, I'm going to put 0. I'm going to offset it. Put 0 on this side. I've got 0. And now I also want to label 2 and 1/3. Let's say that I have 2 1/3 here. One-third, and I'll put 2 and 2/3 over here. But somewhere in between, somewhere halfway in between, there is another value. That's what the density property is telling me. So how do I solve this? How do I go about finding this out? Basically, what I'm going to do is take the average of both numbers. I'm going to add 2 and 2 together. So 2 and 1/3 plus 2 and 2/3. Well, 2 plus 2 is what, guys? 4 plus, because 1 plus 2 is 3 over 3, which is what? 3 over 3 is 3 over 3, which equals 4 plus 1, which equals 5. Guys, how do you take the average of something? Divided by what? Divided by what? How many numbers do I have here? 2 different numbers, so I'm going to divide both of these by 2. I'm just keeping it consistent. Oop, that last one messed up on. What's 5 over 2, guys? Yes, ma'am, Alex? What's 5 over 2, Alex? You do know. Well, if you don't, we're going to do long division and solve it. All right, let's do this, Alex. You're up. Well, let's find out. 2 goes into 5 how many times? That's 2, which is 4, minus make it 1. 2 goes into, drop my 0 and add a decimal. 2 goes into 10 how many times? So now I have 2.5. Just finish and solve this real quick. Now I have 0. So it is 2.5. This equals 2.5. So therefore, the density property says, between any two real numbers, there is another real number. So now this value has got to be 2 and 1/2. Hey guys, real quick, look up here, scrolling up. If that works for real numbers, you've got to understand this. This is huge. It works for rational numbers. We were just dealing with fractions, right? However, it does not work with integers, and we're going to look at why it does not work with integers right now. And here's the reason why. It works with fractions, we just saw that. But here, what about with integers? Well, give me some integers, guys. Look at your notes and give me some integers to use. 1. Give me another integer to put on here. 2. Give me another one. 3. Give me another. 4. Okay, here's what they're saying. Here's what they're saying. This is why it does not work with integers. Say that I want to know what integer falls between 2 and 3. Well, the integer that falls between 2 and 3, I can't figure out because there is no integer between 2 and 3. Do integers have decimals? Therefore, there's no integer. The density property does not work for integers, but it does work with rational numbers, and it does work with real numbers. Alrighty, that's all we got. Your homework is up on the table up front. You can start on your homework.